This problem is the fourth problem in the probability review. Read the question before you play the video. So when you read the question, this must sound very familiar to you. We've done several problems in the problem sets in class for homework, on the in various assignments we've come across this sort of problem. And this type of problem will definitely be on the test. So let's first list all the probabilities, and that's what you need to do in any problem related to probability. Whatever is given, whatever probabilities are given, uh, at the beginning of the problem, write them down clearly in mathematical notation. So later on, when you need to plug in numbers into your formulas that you're going to use, it'll all be very easy because it's already given to you. So let's look at this problem. Alicia is being tested, so there's always a rare disease for which you're being tested. 0.1% of the population actually has the disease. So 0.1% is 0.1 over 100. So shift the decimal point 2 places to the left to convert it to a decimal. So P of D, disease, is 0.001. So probability that someone has the disease is 0.001. Now immediately write down the opposite. What is the probability that someone does not have the disease? That is 1 minus 0.001. Note that if it's a 0.1%, then it would have to be 0.001 as a decimal. Now the next table gives us all the other information that we need about this test. So the information that's given to you is the result of some sort of a clinical trial process, let's assume. So if you have a group of people that actually have the disease, how many of them showed positive, or what percent of them showed positive and what percent of them showed negative, is given in the first row. So how do you write this using probability notation? So 0.99% showed positive, but what do we know about them? We know that they have the disease. So knowing that they have the disease, the person shows positive 99% of the time. So what is the probability that they'll show positive, knowing that they have the disease? So if you just remember that you know that they have the disease, and these two numbers in the top row are related to the group that actually has the disease. So 0.99 is equal to probability of positive given disease, which means they show positive, but we know that they have the disease. So again, the next number is 0.01. What's the probability that they will show negative, knowing that they have the disease? So the number 0.01 is the probability that they'll show negative, but what do we know about these people? We know that they have the disease because they're coming from the first row. Now, the next one is disease absent, which means they do not have the disease. So 0.015 is the probability that a person will show positive. But what do we know about the person? We know that they do not have the disease, which means no disease, disease absent. So probability that they'll show positive, but what do we know about these people? They do not have the disease. So remember that the first two rows are rows related to two different groups, one that has the disease and one group that doesn't. So the second row is the one that doesn't have the disease. What is the probability that they'll show negative when we know that they do not have the disease? So the probability that they'll show negative is going to be high, that's 0.985. So once we've written this highlighted, everything that's highlighted is something that you'll have to write down yourself in the problem. And if these numbers are written correctly, most likely the rest of the problem will go pretty well. So the first question is, what is the probability that Alicia, a random person, tests positive? And nothing else is given. So first write down what we need to figure out. We need to figure out the probability that a random person will show positive on that test. So first we have to think about the two possibilities, because a person can show positive when they actually have the disease, but they can also show positive when they do not have the disease. So we have to consider two cases here. A person has the disease and shows positive, or the person does not have the disease and still shows positive. Now remember the formula for probability of disease and positive. So it's the AND rule, so AND goes with multiplication. But we need to use the rule for events that are not independent. Having the disease and showing positive on the test are not independent of each other. That should be pretty clear, because the probability of showing positive will depend on whether you have the disease or not. So these are not independent events. So we use the rule for events that are not independent, but it's the multiplication rule. So probability of the first times the probability of the second. So that part is the same for both independent events and events that are not independent. But in the case of events that are not independent, you can't just stop here. You have to say, given that someone has the disease, which means that the first event actually took place. So it's easy to remember the formula, although I'll give it to you on a test. If you understand the meaning of events being not independent of each other. So probability of the first times, because it is AND, probability of the second given that the first event happened. So using the same formula for both, we have probability of no disease and positive is probability of no disease times probability of positive given no disease. So when you look at these probabilities, you've already thought through this and you already have all the numbers. Look for the highlighted numbers. You have to just plug them all in and get a number using your calculator, final answer using your calculator. So 0.01598 is the answer, which means 1.598% of the random of the population will show positive, which means if a random person takes the test, then the chance that they'll show positive is 1.598%. Even though, if you see, there's only 0.1% of the population that actually has the disease, 1.598% will test positive, which means that there are a lot of false positives in this test. In the second part of the question, let's read the question, and as we're reading it, let's write down the probability that we need to figure out. So what is the probability that Alicia, a random person, has the disease given that the person tested positive for the disease? So as you're reading it, write down the probability that you need to figure out. It is a conditional probability, and we've come across this in a previous problem. How do we use the formula here? We have a numerator and a denominator. If it's a conditional, the probability of having the disease and showing positive, which means both, goes in the numerator, and the probability of the second event goes in the denominator. So if you understand the pattern of this particular formula, then it's easy to write down the interpretation of the rule quite easily. The AND goes in the numerator. The probability of the AND goes in the numerator. The probability of the positive goes in the denominator. So now just write down your formula. Remember, we've already done this as part of the previous part of the problem. So we just basically copy that probability of D and probability of the second event given that the first event happened divided by probability of positive. Now there's no new work that you need to do here. As long as you've figured out the formula you need to use, the probability of positive comes from the previous part. The numerator also comes from the previous part. It's just one small portion of it. Just plug them in and you get your final answer using the calculator. So if you think about it, if someone goes in for the test and shows positive, what is the probability that they actually have the disease? And here it turns out that it is 6.19%. So 6.19% chance that you actually have the disease when you've already tested positive for it. Now that is probably not a great test. So this is how a problem of this sort is done. It's a clear pattern. You need to see that. And sometimes we think that we understand the problem, but then when we go down to writing the solution, it gets confusing. So it's a good idea to think through this on your own, write it up, and see if it makes sense.